Hello, today we will talk about dynamics, new chapter. So let me give some small, quick, main details, then we will continue our lesson. So till this chapter, we explained about kinematics. In kinematics, we usually worked about velocity, time, acceleration, distance, displacement. If you paid attention, we didn't ask this kind of questions. For example, why is this car moving with this a certain acceleration? We didn't ask. It was given, or we need to find this acceleration. Actually, this acceleration depends on the force, and this chapter, dynamics chapter, will answer for this question. So shortly we can say dynamics, this is a chapter which is related to the forces. You have a force, that's why something will move, it will accelerate, and some part will be related to the kinematics. Mainly in this chapter we will study forces and how these forces creates acceleration. As you know, dynamics basically this is Newton's law. We have three laws: Newton's first law, second law, third law. The main part that we will be using, we will be working, for in this course is basically Newton's second law. When you hear dynamics, when someone says Newton's law, this is related to the Newton's second law. Newton's first law is actually related also to the Newton's second law. If you know the Newton's second law, it means you can easily explain or you can understand the Newton's first law. So for this reason, let me explain Newton's second law. As you know, Newton's second law is the relationship between force and acceleration. When you increase the force, acceleration will increase. If you decrease the force, acceleration also decreases. So there are so many experiments, and we will not explain the experimental part. We will just give you the ready mathematical relationship between force and acceleration. As you know, this equation is this one: force equal to ma. F is a force, but be careful, this should be resultant force, or sometimes we call it net force. Net force. So net force, resultant force means first of all you should find resultant net force. If you have more than one forces, it means first of all you should find, by using vector addition, summation of vectors, because force is a vector, the resultant vector, and that object will move in the direction of the resultant force, resultant vector. So this part is very important. So basically you need to repeat what you studied about the vectors, because force is vector, and to add two forces, it means you should remember how to add two vectors. For example, m is a mass, a is a acceleration. As you see, very small equation, but it's very important equation. So basically we will learn how to use this equation. Before using this equation, let me shortly explain forces. So as you know, there are so many types of forces, but in general we can divide or we can consider forces as two groups, two main types. The first type is contact forces. As it says, contact means if force appears due to the contact, direct contact, it means we can group it as a contact forces. For example, force in the rope or on the rope. You have a rope, you are pushing something with the help of the rope. It means there is a force on the rope, so we call it tension. So tension is a contact force. Reaction force, for example, you are sitting somewhere on the chair, for example, chair is holding you, it means chair is applying a force upward. That's why we are not falling. So this reaction force, sometimes we call it normal force, also appears due to the contact. Friction force, for example, yes, friction force also appears when there is a contact between two bodies. And the second group, non-contact forces. So forces that appears without contact. For example, gravitational force, as you know, force between moon, earth, for example. We know there is a force. That's why moon cannot escape. It's rotating around the earth. Why? Because there is a gravitational force. But there is no direct contact between moon and earth. There is a kilometers, a very huge space. But we know that there is a force. Otherwise, moon will not rotate the earth. It will escape. So we can say that gravitational force is a non-contact force. For example, magnetic force between two magnets, it can attract each other, it can repel each other without contact. So magnetic force also is an example for the non-contact forces. Electric force, forces between charges, positive charge, negative charge, attracts, repels, without direct contact, as you know. So electrostatic force is also example for the non-contact forces. This is just general information, just to know it, to remember it. Now, F equal to ma, force equal to mass times acceleration, and we said force here, it should be resultant force or net force. Let me give you a quick example. Let's say we have a small body and we have two forces acting on this body. F1, let's say 2 newtons, and the second force F2, let's say it is applying in this direction, F2, and let's say equal to 3 newtons. So we have two forces, 2 newtons and 3 newtons, for example, as shown in this figure, and these two forces acting on an object. And we know that this object will move under influence of these two forces. The question is at what direction it will move and with what kind of acceleration, what will be acceleration of this object. In order to answer for this question, we need to use Newton's second law, F equal to ma. But first of all, we need to find the resultant force. F1 is a vector, F2 is a vector, and you know how to add these two vectors, yes? You can use component methods, you can use triangle methods, it's totally up to us. For example, let me use triangle method or parallelogram method, we call it. So this is the first vector, F1. Let me bring the tail of the second vector and let me join it with the head of the first vector. So this is what we will do approximately. So, and this will be resultant vector, yes? Let's call it R. And it will be equal to something. It's not important for now. And this direction of the resultant force, this direction is basically direction of the motion. It will accelerate in this direction. So it means we need to use this value in this equation. We need to use this value for resultant force, and we need to take it, we need to bring it to the Newton's second law equation, F equal to ma, and from here you can find acceleration, and this object will accelerate in this direction. So roughly it will accelerate in this direction, and this acceleration equal to resultant force divided by mass according to the Newton's second law equation. And according to this equation, let me create new page. F equal to ma, this is a Newton's second law, and now I will explain Newton's first law. According to this equation, if you have a zero resultant force, then acceleration will be equal to 0. F equal to ma, 0 equal to ma. So mass cannot be 0, of course. We have an object. Only acceleration can be 0. So basically, object will not accelerate. It's very simple. What does mean acceleration equal to 0? It means velocity will not change. Velocity will be constant. Acceleration 0 means velocity will not change. It will not accelerate, it will not decelerate. Constant velocity. So if you have an object at rest, initially 0 velocity, then velocity will be 0. Stationary object will not move because velocity constant. If you have something, object, which is moving with a certain velocity, let's say 10 meters per second, and if you have a resultant force acting on that object equal to 0, it means it will keep moving with the same velocity. It will not change its direction. It will not change its speed. It's obvious because according to this Newton's second law, yes, F equal to ma. So basically, if you don't touch, or if you have a resultant force equal to 0 on an stationary object, it will keep its position. It will not move. If you have a resultant force equal to 0 on an object which is moving with certain velocity, it will keep moving with that velocity. It will not change. So basically, this is a short and a simple explanation or definition for the Newton's first law. Newton's first law means Newton's first law basically comes from the Newton's second law. Now let's come to the Newton's third law. This third law is also very simple. Shortly we say action-reaction. For example, as we said, if you remember in previous example, we said that there is a gravitational force between two planets, yes? Earth, Moon. Earth is attracting the Moon with certain velocity. I'm not sure about, I don't remember the magnitude of this force, but there is a force. The same force is acting on our Earth. It's absolutely same value, same magnitude, but in opposite direction. And we call it basically Newton's third law. We explain it with Newton's third law. For example, you have a rope. If you apply force to the one end of this rope, the same force will be same force you need to apply to the second end of the rope to keep it stationary. So basically, you have same forces in opposite directions, and Newton explains it with its own third law, Newton's third law. So shortly we say action-reaction. Let me draw it quickly. Let's say this is Earth, this is Moon, and Earth is attracting the Moon with, let's say, force F1. Moon also attracts the Earth with force F2, let's say. In terms of vector, F1 equal to negative F2. Negative means just opposite direction. In terms of just magnitude, just number value, F1 equal to F2 in terms of number. And this is Newton's third law. Very simple. Now we will focus on Newton's second law, which is F equal to ma. This F should be resultant force. In order to find the resultant force, you need to use vectors, addition, submission of vectors. But the important thing before adding forces, we should make sure that we are considering all the forces. Basically, you should not forget any single force. If you forget one force, then you will get wrong answer. That's why the first step is very important. Find and draw with right, correct directions all forces. You should find, draw with right, correct directions the forces. You should not forget any force. So basically you need to draw. You need to draw the object, you need to show all forces with correct directions. And we call it just free body diagram. The figure, the diagram with correct directions for forces, and this diagram has a special name. We call it free body diagram. For example, let's consider an object on the plane surface, on horizontal surface, and someone is applying horizontal force. So this is a surface horizontal. We have an object mass m, and someone is applying force to the right. So only one force is given, and we need to solve this problem, for example. Before solving this problem, we should do free body diagram. We should draw free body diagram. So let's do it. Basically, how many forces acting on this object? In this example, in this simple example, we have 3 forces. Of course, if we ignore the friction force. The first one is shown on this diagram, on this figure, force acting onto the right. This object has its own weight. mg, it's always downward, yes? And the surface table is holding this object. If you remove this table, it will fall down. At the moment, it's not falling down. It can move only in horizontal direction. And there is something that is holding this object. And this force, we shortly call it no reaction force or normal force. That's why it cannot go downward. It cannot move downward. So that's all. We did free body diagram for this simple problem. So you should remember, please draw free body diagram for each object. Let's say you are solving one problem and you have 3 objects, and you should draw 3 free body diagrams for each one. I mean, 1 free body diagram for each object. You have 3 objects, 3 free body diagram you need to draw. Only in that case you have a chance that you'll get correct answer, right solution. Let's continue this example. Let's say mass of this object equal to 2 kilogram. Let's say force equal to 20 newtons. So far, let's find acceleration. Let's find normal force, reaction force. Again, it's better to draw axes, x, y axis, as you know. So vertical y, horizontal x. Basically, you can apply Newton's second law in both directions, in x direction, also in y direction. So, for example, resultant force in x direction equal to ma acceleration in x direction. Also, you can apply the same force, same equation in vertical direction. So F resultant force in y direction, in vertical direction, also it can be equal to mass times acceleration in y direction. So here you should think, we know that this object cannot fly upward. It cannot go into the table. It's obvious, it's simple. It means it is not moving in the vertical direction. If no motion in vertical direction, it means no acceleration in vertical direction. So it means we can rewrite this equation. The resultant force in vertical direction should be equal to 0. Now let's find the resultant force in vertical direction. We have two forces, normal force and weight, and they're opposite to each other. So normal force minus weight, this is the resultant force basically. This is the Fy, should be equal to 0. So from here we can see that normal force, reaction force equal to weight for this situation. Now let's study this object's horizontal motion. So resultant force in x direction should be equal to mass times acceleration in x direction. And how many forces we have in horizontal direction? If we pay attention to this diagram, we have only one force. And so this force will be resultant force in x direction, equal to max. This object moves only in x direction, so that's why we can write just ma. Instead of ax, we can say just a, because this object is not moving in different directions. We have only one acceleration. So force equal to 20, mass 2, acceleration a. So this acceleration equal to 10 meter per second square, for example. It will accelerate to the right with this acceleration. Normal force equal to mg weight, which is 2 kilogram, and it will be 2 times 10, gravity approximately 10. So normal force will be 20 newtons. This is how it works. This is how you need to solve the problems. Of course, this was a just simple example. We will make it a little bit difficult further. Another example, let's consider two objects instead of one. We have a horizontal smooth surface. Smooth means no friction. And we have two objects connected with a rope. And we have a force to the right, for example. And this force equal to 100 newtons, M1, M2. Let's say M1 equal to 10 kilogram, M2 equal to 30 kilogram. We need to find acceleration, for example, and the tension. Tension is the force on the rope, basically. And we use special symbol T because of tension. It's coming from word tension. It's a force, basically. How we can solve this kind of examples? I agree that this is a simple example, but we need to practice the method how we need to solve. And we say that it's better to consider each object separately. So basically we need to draw free body diagram for each one. So let's start with first object. How many forces acting on this object? M1. Weight M1g downward. Reaction force, normal force upward. Let's call it N1 because we have a second object. There is a force to the right, 100 Newton, and the rope is trying to stop this motion. So there is a rope, there is a force, and direction will be to the left because it will try to stop it, and we call it just T. No friction, smooth. As you see, we have only 4 forces: force, tension, weight, normal force. And we know that this object is not moving in vertical direction, and we can say that normal force equal to M1g, as we explained it in previous example. Very simple. And which is equal to 100 newtons. And again, this object can move only in horizontal direction. It's obvious. So it means we need to find resultant force in x direction, in horizontal direction. Actually, we need to write in this way: resultant force in x direction equal to ma x acceleration in x direction. But we know that it can move only in x direction, so let me keep it simple. Just resultant force equal to ma. Resultant force, this F, don't confuse it with this one. This force means resultant force. This is the original equation. Or let me write in this way, maybe it will be better. Resultant force equal to ma. Resultant force for the first object is, as you see, F minus T. Force 100 Newton is trying to move it, but we have a tension which is trying to stop it. It means opposite direction, so that's why we subtract it. And this should be equal to M1A. M1 because we are applying Newton's second law for the first object. Now, force is 100, tension unknown, mass M1 is 10 kg, acceleration unknown. Now let's draw. So you see we have one equation but two unknowns. We need one more equation. Now let's go to the second object. Let's draw free body diagram to the second object. We know that second object will move in the same direction to the right. Why? Because there is a rope. The same rope which is trying to stop the first object will try to move the second object. Same tension because same rope. Basically, tension will be directed to the right for the second object. And we have a weight M2G, and of course there is a normal force N2. Again, it will not move in vertical direction, so N2 reaction force equal to weight, which is 300 newtons. Now let's apply Newton's second law for the second object. So again, the resultant force should be equal to ma, and it will move in horizontal direction, so we need to pay attention to the horizontal forces. And as you see, we have only one force in horizontal direction, which is just T. So this tension equal to M2 because we are writing to the second object, acceleration. So here you should remember that these two objects will move with the same acceleration because of the rope. This is not a spring, this is a rope. It means if you move first object, for example, for 1 meter, second object also will move for same 1 meter. It means they have the same velocities at any time, and they will have same accelerations at any time. So tension, of course, unknown. Mass of the second object is 30 kg. Acceleration unknown. This is a second equation. This is our first equation. Two equations, two unknowns. In terms of mass, we can solve this problem. So let me take tension into the from the second equation into the first equation. Let me substitute it. Acceleration 2.5, tension 75 newtons. So we consider two objects, motion of two objects under the influence of force, horizontal force, and it was horizontal motion. Now let's consider the similar problem but in vertical motion. So let's say we have two objects connected with a rope, vertical connection, M1 and M2, for example, and we have a force applied to the first object upward. Let's use same 100 Newton. M1 equal to 2 kilograms. M2 equal to 3 kilograms. So question, find acceleration and tension. Again, Free body diagram, very important. We have two objects, we should draw two free body diagram. Let me start with object number 1, M1. How many forces acting on this M1? 100 Newton upward, it's already given, shown. And we have a weight of the first object, M1G, of course, downward. And there is a connection, there is a rope, and of course this rope will try to stop this M1. M1 is trying to move upward, but rope is trying to hold it. It's trying to stop it. It means it's obvious that tension will be directed downward. So we have three forces: 100 Newton upward, tension downward, weight downward, M1G, weight downward. This is a motion in vertical direction. So actually we should write like this: Fy, resultant force in y direction, equal to MAY, acceleration in y direction. But let's keep it very simple. It will not move in horizontal direction. So there we have only one acceleration, which is in vertical direction. So let me call it just A instead of AY. So resultant force for the first object equal to mass of the first object times acceleration. Resultant force for the first object is equal to force times minus tension and the minus weight. This is the resultant force. Upward force, tension downward, weight downward. It should be equal to M1A. So force 100, tension unknown, weight 20, 2A. So 80 minus tension equal to 2A. Again, we have one equation, two unknowns. We need one more equation, which is coming from the second object. Now let's come to the second object. Let's draw free body diagram. Of course, this second object will move upward because rope is applying force upward. And this force, of course, tension, same tension. Downward, we have its own weight. So resultant force 2, resultant force acting on the second object, should be equal to mass of the second object times acceleration. Again, these two objects have the same acceleration because of the rope. If you move the first object for 1 meter, second object also will move for 1 meter. Again, as I explained in previous example, these two objects will have same velocity at any time and the same acceleration. Resultant force for the second object, tension minus weight. Tension upward, weight downward, that's why minus. M2A, tension unknown, weight of the second object 30 newtons equal to 3A. So we have two equations and the two unknowns. We can solve this problem. So let me bring second equation here. Tension minus 30 equal to 3A. Let's add these two equations. So tension will be cancelled. 80 minus 30. This part is just mass. You can skip it actually. 2A plus 3A, or you can use different method. 50 equal to 5A. So acceleration will be equal to 10 meter per second square. It will accelerate with acceleration 10 upward. Now, once we have acceleration, we can come back to the first or second equation in order to find tension. Let me choose equation number 2. So tension minus 30 equal to 3A. Tension minus 30 equal to 3 times 10, acceleration equal to 10. So tension equal to 30 plus 30. So tension equal to 60 newtons. So this is the answer for the tension. So let's summarize. Draw all forces acting on each object. We call it free body diagram. then just simply apply Newton's second law. Resultant force equal to ma for each object. That's all.